Yeah. Yep. Probably, yeah, it'll be due Wednesday. So you'll have, so if you want to get with your group, you can, after lab or before lab or sometime. Oh, I've got my fall classes are now available. Interesting. I apologize for this. I've got to do this or I'll forget. Hey, Brittany. There we go. I had to make sure I had got my 2 take-home tests entered. Hadn't done that yet. All right. Last time we had a interesting talk on waves, on electromagnetic waves. So that's where we are. And waves pretty much travel. What's their speed through a vacuum or through air? Speed of light, right. They travel at the speed of light in a vacuum or through air. And we looked at that one slide for quite a while because I kept thinking of things about it. And the speed of light is measured this way. The frequency times the wavelength, the actual wavelength. You might be going, well, what is a wavelength? You know what a wavelength is? Mathematically, I'll show you. Wavelength looks like this. There's a wavelength. As it goes from, or I could have done it from here to here. Is also a wavelength. This too is a wavelength. Okay. In other words, how the length of time, the length that goes from here to here. What is that length? That's lambda. Okay. And this thing here is a length too, lambda. All right. It's a length because, and it's kind of funny because it is a length in meters, and frequency is 1 over seconds, and so the units work out right. So you get meters divided by seconds, which gives us meters per second, which gives us the what the wavelength is. Okay? Now, there's one other thing. Maxwell, Scottish scientist back in the 1800s. Maxwell hypothesized this, and it's actually been proven that the speed of light also equals this. I was going to have you do this on your calculators, but thought not. Thought better of it. Is equal to mu naught, permeability of free space, times E naught, the permittivity of free space. Multiply those two together, take the square root, take the inverse of it, you've got the speed of light. Kind of an elegant little thing. Okay. All right. Today we'll get through chapter 24. We will talk about the Doppler effect. We'll talk about the energy contained in a wave. Because remember, I ended the class a little bit last time with that a wave is really a way to propagate energy without moving matter. All right? Without moving matter. And the first thing we learned was that an accelerating particle is what emits a wave. Okay? So, on a wire that's attached to an AC current, you've got the current going up and down like this. Well, it's accelerating because it's changing direction, so therefore it creates an electromagnetic wave that goes out. The B field is perpendicular to the E field. Both of them are perpendicular to the wave. Okay? So, if the wave is moving straight, then the E field becomes my thumb and the B field becomes my middle finger, and it's kind of like they're flopping back and forth like this or whatever. Okay? That makes them a transverse wave. Because the E field and the B field are perpendicular to the direction of the wave, that makes them a transverse wave. Unlike a longitudinal wave, which is sound, which the wave moves, nothing is, it's parallel to the things making the sound are parallel to the direction of the wave. Okay? And a regular wave in water on the beach is both. It's longitudinal and transverse. Okay, so those are the basics from yesterday. Now, let's talk about electric energy density. Because if something, let's just think of our good old sun. Okay? Good old sun. It emits a wave. Most of it's traveling through space, which is a vacuum. So no sound comes. We can't hear the sun going burning and blowing up and booming and everything else because can't hear it because it's not. It's a vacuum. But we can sure see it and we can sure feel it. We can sure feel the radiation from it, especially I think today and tomorrow. But then the rest of the week is going to be really nice. But anyway, if we think about it, it's sending out this energy, this electromagnetic radiation, which in the form of heat, in the form of light, and all kinds of other things. It's sending it out in a big ball that's like a big sphere, right? Think of concentric spheres. As we're moving away from the sun, we're passing through all these concentric spheres. And so that's why we call it the electric. This is why we call it the electric energy density. Okay? This is why we call that the electric energy density, because it's a three-dimensional thing that the energy is going through. It's not a linear thing or a one-dimensional thing. And so the electric energy is what is known as the electrical energy per unit of volume of that concentric sphere. Okay? Electric energy per volume. Let me put electric up here. Electric energy. It says electric energy per volume. And that equals this. We found this out. I was supposed to put this down when we were looking at capacitors, but you all wanted to get away from them so fast, I think I forgot. But anyway, there's the energy. That's the energy, the average energy density contained in, now that's the energy density in a, so that's joules per meters cubed, all right? Joules per meters cubed. Okay. Magnetic energy density, same thing. Hopefully this marker works better. Magnetic energy density, same. Except it's magnetic energy over volume, which will equal, this one's a little bit different, B squared over mu naught times 2. That's a bad way to write that. Over 2 mu naught. Okay? The permeability of free space for magnetic field, due to the mathematics of setting it all up, winds up in the denominator. Okay? All right. So, each carries an equal amount of energy. All right? Each carries an equal amount of energy. So therefore, the energy density of each one could be written this way. We'll say U is our total energy. Density. Energy density. Sometimes we get lazy and we drop the density part, but it's not in joules, it's in joules per meters cubed. Total energy density, I can just write as E naught E squared. Because the total energy in the system would be 1/2 E naught E squared plus 1 over 2 mu naught. I'll write it this way so you can see it. B squared. Now, the magnetic field and the electric field at a certain time as they're leaving have carried the same amount of energy. Okay? They carry the same amount of energy. So I can say that since this quantity is the same as this quantity, in other words, I've got 1/2 E echo naught squared equals 1 over 2 mu naught B squared. Since those two are the same, cancel the 1/2s. I can just say that E naught E squared equals B squared over mu naught. I can say that. That's by experiment and by theoretical physical things, we can say this. So I can also say that U, like I said, this lecture is kind of algebra heavy, equals B squared over mu naught. Okay? So far, nothing useful for you all in doing any kind of homework problems or something like that. But there's a cool thing that comes out of this. Let's set these two guys equal. Let's set this equal to B squared over mu naught. Keeping this guy in mind right here. Keeping this guy in mind right here. So if I square this, C squared then equals 1 over mu naught E naught. All right? So I'm going to say that E squared then equals B squared, just divide through by E naught, over mu naught. 1 over mu naught times E naught is equal to C squared, so I wind up with this. E squared equals C squared times B squared, and so the electric field equals the speed of light times the B field, which is kind of a cool result. It's true. You know why it's true? Because the algebra says it is. No, it's true. Because we experiment. Okay. All right. So that's kind of a neat little result. Now, let's look at and if we want the average, I will find a good marker here in a minute. Here we go. What were we talking about? The average energy density. Since this is moving about in a sinusoidal way, in other words, electromagnetic waves move like this, we're going to have the maximum energy is going to equal, well, we're going to have the average, the root mean square energy is going to equal the maximum energy divided by the square root of 2. And the same thing with BRMS. Do the maximum and square root of 2. Okay? So like right here with the E field, to find the average of all those, since it's sinusoidal, this would be the max. This would be E naught right here. Okay? All right. Now, this next thing is actually kind of what showed up on your lab when they're talking about the magnifying glass and burning the hole in the sun, but that's actually moving on more to chapter 26, actually. Which we will talk about shortly. Not today, but we will cover parts of 26 and get a big chunk of 25 done on Friday. All right, but today is this one. So, intensity. All right, so intensity is how much power is passing through a perpendicular surface. We'll just take, like, remember way back, chapter 18, when we took those Gaussian surfaces, again, concentric shells around something? Okay, what we want to know now is how another way to measure the intensity of the sun or the intensity of a light bulb or something like that is this way. The intensity just by your own, because you are a Homo sapien, you are a natural physicist, you know that the further away you get from the light bulb, the less intense the light is, right? The closer you get, the brighter it gets, and you can actually start feeling the infrared heat coming off of it too. All right, but the intensity is given as this. S equals the power divided by the surface, divided by the perpendicular surface area that you're moving through. Okay? In other words, again, I take a light bulb, I put all these concentric shells around it, and that surface that I'm moving perpendicular through that surface as my wave is going through, puncturing through it. Okay? And so the surface of a sphere is 4 pi r squared. But the power, what is power? How do we measure power? Energy per time, right. And so this is a funny looking thing. Intensity is measured in watts per meter squared. Watts per meter squared. And we will get to the polarization equations and all that here in a minute. All right. So it's that's the power. And as I move further away, it gets in other words, as I move further and further away, and the R, let's just say R is 4 pi r squared. That's the surface area of a sphere. As R gets bigger and bigger, as R grows bigger and bigger, what happens to my intensity? It gets smaller and smaller, okay? Because I start off with an initial power coming from the sun, joules per second that it's shooting out there, okay? And as I get further and further away, the intensity goes down, which makes sense, okay? That makes sense, all right? But, so let's take a look at this. So we can also say this is, how did we say this? Oh yeah. It's the total energy divided by time, which is power. Energy divided by time is power times the area, like that. So basically what I have is this. I've got mu, or I've got U over T times A. Okay. All right. Now, to get the total energy, though, total energy has to be this. Remember, total energy. This is kind of put your pens down on this one. I'm just gonna we're just gonna wave our hands here a little bit. Remember from earlier, the total energy is equal to the energy intensity times the volume. Okay? Times the volume. All right. So this total energy is not U. That's where I screwed up. It's still this total energy. Because it's not the energy density. Okay, the total energy, though, is equal to the energy density times the volume. All right, that's what we got earlier. That's why I asked you to put your pens down, because I made a mistake. So, oh, this is good. Let's just write the same thing twice. Very good. All right, it's because I got ahead of myself. Now then, so if we take the total energy, if we take the energy intensity, the energy density. We take the energy density times the volume, I get the total energy. Well, how do we get the energy density? We do this. It's U times some meters cubed. Okay? Well, here's how I get the meters cubed. Okay, if I'm traveling through, for simplicity's sake, let's say my electromagnetic wave is going to go through this little volume right here. Okay? Now this length is equal to speed of light times t. All right? And the area is equal to the surface area of, which is 4 pi r squared. Or it's just equal to the surface area. So my volume, this is equal to length, volume is equal to area times length. So here we go. So we get CT times A. So up here on top, we get mu naught, or we get U, which is the energy density, times A times CT over TA. And so it winds up that we get the intensity is equal to U times C. Whew. The intensity is equal to U times C. What kind of problem could you expect from that kind of thing? Okay? What kind of problem could you expect? Oh, let's look at, in fact, I'll probably assign this one. Problem 23. It says the microwave radiation left over, in fact, let me circle that so I make sure that I assign this since we're going to go over it. Since I've already lost you, I can tell. That's why I'm going to do a problem and get you back here. All right? So what can we expect? The big idea is the light bulbs put out a lot of energy. They're putting out energy, okay? And the further away we get away from them, the intensity of them goes down, all right? And the closer we get, the intensity goes up, all right? And there's certain ways you can measure it, all right? So that's the big idea. All right, so now it says microwave radiation left over from the Big Bang explosion of the universe has an average energy density of 4 times 10 to the negative 14th meters cubed. Okay, so the average energy density, U, is equal 4 times 10 to the negative 14th joules per meters cubed. Okay, that's the average energy density. 4 times 10 to the negative 14th joules per meters cubed. What is the RMS value of the electric field of this radiation? Okay, so what we've got to do is we have to find ERMS. And since this is the average, U is equal to E naught times ERMS squared. Oh, well, this isn't going to be too bad. This is pretty simple. Oh, I was hoping. Okay, well, you can get it. You can get it freebie. It'll work. I guess it seems simple to me because I've worked with this a lot, and so I just kind of knew this. If you didn't know that, you'd be kind of stuck. So basically, you got this. You got so U equals E naught times ERMS, and so U over echo naught is the square root of it is equal to ERMS. And you should get our good old newtons per coulomb when you do that, hopefully. Or volts per meter. What's that?
Like, what's the value for
What is the value for E? It's in other words, what are the units? It's either newtons per coulomb or volts per meter. One of those. All right. Okay, and 25 would be a good problem too for this. It says the average intensity of sunlight. So here we get into the average intensity. The average intensity of sunlight is 1,390 watts per meters cubed. Okay, that'll work. What is the maximum energy that a 25 meter by 45 meter solar panel, let's say watts per meter squared. Okay, so they want to know what is the amount of energy that a 25 meter by 45 meter area is equal to 25 meters by 45 meter thing. Okay. All right. Could collect in 1 hour. And T is equal to 3,600 seconds. This is a better problem. This is a nice little problem. Okay. So that's the intensity that we get. So we know this. We know that S is equal to power over area. Okay? And we know that power is equal to joules per second. So we'll say, okay, well, S then is equal to joules per second over this area. Oh, so we'll just go, well, this will work. SA then equals power, or joules per second, some joules per second. Now then, if we let T go to 3,600 seconds, the amount of energy it will collect as joules would equal SA times T. Okay. That's all fine and good. Now for a paid political announcement. No, it's not a political, it's just a science. You only get about 15% of the energy of all this energy. And most of them were talking about material science type things that were, but that's what our guys do downstairs, is we got to find materials that work not only in solar energy but in other things smaller. Because they've actually come up with some solar panels that are almost like a thing, and they're about 20% efficient, and they're actually fairly cheap. The problem, I would need to have saran wrap over Johnson County, all right, to be able to provide power to Brookside, all right. So where would this work? So you think, well, where would this be effective? Oh, maybe somewhere in Saharan Africa. They could get power pretty cheap that way. Would it work in New York City? No, because there's no place to put all that stuff. So those are the, yeah, that's all the give and take of, so solar energy actually may not be the savior for the United States. We might just burn nasty coal and do these non-fixes of swapping carbon back and forth for a long time. But that's the big problem with climate change, is industrial revolution that they're going through, their boom, where their standard of living is increasing just like ours. Basically, they're going through what the United States did between after the Civil War until 1929, is what they're doing, okay? And we can't deny them that standard of living increase But the problem is they're building 1 gigawatt per week coal-fired plants, all right, which is dumping a lot of nasty carbon into the air, okay? But China, they have an amazing way of being able to tell their citizens, when they make up their mind to do something, they have a good way of telling their citizens, this is what we're going to do, and it works. Like, nobody's going to drive for 2 weeks before the Olympics so we get the air clean. Guess what? Nobody drove, right? They can do that, all right? So, anyway, I kind of got off track there, but kind of went into my physics for future presidents class there. But so that's the real issue behind solar panels and all that kind of stuff, is they're very expensive. Last question. This is all not related to the subject, but it's the stuff you're going to remember when the course is over. What country has the largest oil reserves? Venezuela? Right. For what country? Saudi Arabia? No. Somebody said Canada. Canada is a close second to the United States. No. They do. Here's the deal. Here's the deal. And I'll try and hide some bias here, but here's the deal. We've got more oil. We've got 4 times more oil underneath our country than Saudi Arabia does. 4 times more. Okay, right? Yeah. Emily's like, what? You're kidding? No, we have plenty of oil to meet all of our needs for the next 300 years. Okay. The problem is, it's in shale. Okay, and it's very expensive. If we said no more imports, all of a sudden, that's average. We don't want to do that. We don't have the will to do that. It's much easier when things are around here. In Europe, they've been here forever. In Asia, they've been there forever. Okay? What? So, therein lies the problem. Now, once oil gets above $40 a barrel, then Canada starts manufacturing their oil. They start drilling and manufacturing it, okay, and start pumping it out. Because then, and as a matter of fact, last year when we were going through this, because of speculators in the market and all that kind of stuff, it shot up. The price, when the price of oil is $137 a barrel, our #1 trading partner for oil was not those sinister people in the Middle East that we always talk about, you know, they're so evil. It was Canada. It was Canada. Because once oil is over $40 a barrel, it becomes very cheap. Or it becomes, they can make money doing it. And the other problem is, if we start drilling here, the profit margins for Exxon and stuff goes way down. That's not good either.
Well, I know like we do drill in the U.S. And
Sure.
like, are there not like, is that not run by big companies? Is that not like larger companies?
Oh yeah, like the Alaskan Pipeline.
Yeah.
Sure, that's good old Dick Cheney and his boys. You know. Oh, let me be vice president, and we'll write the energy policy because I'm the CEO for Halliburton. Oh, that was smart. Okay, but anyway. So therein lies a lot of the problem, is that China needs and India need an incredible amount of energy. And they are pumping energy out, and they are polluting at an alarming rate. Not near what we are, but almost. They're getting there, okay? And the other thing is, the reason the Chinese and the Indian governments kind of bristle at us a little bit is they're like saying, we're not doing anything different than what you did 100 years ago, okay? And you don't have the right to tell us that we can't grow and that our people can't prosper. Right? So, anyway, so it's a prickly problem. That's why you're here, so you can figure it out. So that when I'm old, I still have a place where I can breathe and live. Okay? All right, Nick. Okay. Oh boy. All right, so that was your paid political announcement. It's now over. Hopefully it didn't get too political. It was mostly science and policy, which is good stuff. And we do offer, if you need that 3 hours of science credit to beef up the GPA in science and stuff, we are offering Physics for Future Presidents in the fall. It will be taught by Dr. Tony Caruso, who's a very fun speaker. And put it this way, he's an ex-linebacker. We'll just leave it at that. All right. In college. What's that?
Is it fun to look at?
I guess. That's kind of a loaded question for me. But anyway, all right, let's talk about the Doppler effect. Now, and like I said earlier, last paid political announcement or announcement for the physics department, if you're looking for a minor, we are offering, the rules of the minor are 18 hours, and you need to take 10 hours basically beyond 220, okay? You can't take the problem with Physics for Future Presidents. I wish we'd have numbered it like 221 so that it would count towards minor, but it's not. It's numbered, it's a 100-level course. So that wouldn't count. But we are offering astronomy and stuff like that that you can do. Okay, and our labs too. All right, now, so let's talk about the Doppler effect. Okay, we've talked about the energy. You've seen how a couple problems would work when we talk about the energy density. Now, let's talk about the Doppler effect of electromagnetic waves. This is how, due to good old relativity and due to quantum mechanics, all that stuff that was scientists were, physicists, chemists were wrestling with back at the turn of the century, of the last century, we have all these nifty things. Some of them I don't find so nifty, and those are called radar guns that the policemen have. But anyway, what they do is they give relative frequencies of what's going on so that you can determine the speed of an object, okay? Because it's going to give off a wave, it's going to give off a, in other words, you're going to have an observer, you're going to have a source, and the source of the wave is going to tell the observer what their speed is, relative speed is, okay? And so that's how radar guns work. Now, I'm not going to go into the radar gun problem. We will look at the other problem that I will assign as part of your homework today. All right, so here's the Doppler effect. Basically, it says this. The frequency of the source, I hope I get this right. Or I screwed it up already. I've screwed it up already. I do this every time. Frequency of the observer equals the frequency of the source times 1 plus or minus the relative velocity divided by c. And this works when we have this situation. This works when we have this situation when the relative velocity is much, much less than c. That almost looks like much, much less than c. These are supposed to be those guys. Okay? Or you could almost say, you'd be looking at this, you're probably looking at this going, wait a minute, well, if this is the case, then this is almost 0. Yeah, it is, but there's a very small difference there. Now, what we have to wrestle with here is whether it's plus or minus, whether we choose whether it's plus or minus. Now let me go through what this is again. This is the observer. This is the source emitting the frequency, okay? This is what the observer observes as the frequency, okay? So there's a source frequency, there's the observer frequency, what he sees, he or she actually sees. And then and it's based on the relative velocities of the two to each other. Now we have to decide whether we use plus or minus. We use plus. We use plus if the observer and source are closing the gap between themselves. Closing the gap between themselves. We use minus if the observer and source are increasing the gap between them. Okay. So, let's take a look at this situation. Let's say, here's your observer, and here's your source. Observer is going 34 meters per second. Source is going the same direction, but at 42 meters per second. Closing or widening the gap? Or increasing? This is increasing, so what would we use? A minus sign or a plus sign? Minus. This would be a minus. Okay? Let's do this one. You've got the observer and the source. What are they doing? Closing. So what would we use? Plus. So that's, and this kind of goes into a, and if you're going fast enough, in other words, if all of a sudden this relative velocities between the two, if all of a sudden the relative velocity, this little truism doesn't hold anymore, you're getting close to the speed of light, then what happens is you actually have a complete phase shift in the frequency. And so if you think about that, if you have a phase shift in the frequency, if you're going fast enough, if you run at somebody fast enough, close to the speed of light, and you're wearing a green shirt, it might look red to them. That's why you see that little physics funny t-shirt that says, if my t-shirt is red, you're moving too fast. That's, okay, well, it's a physics joke. All right? Sometimes you got to think about it. Sometimes you just got to let it flow over you. At least I'm not cracking my old, all right, I'll crack one of my old math jokes. My students used to almost throw things at me. You know what the little acorn said when he grew up? Geometry. Whew. Okay. Geometry? Yeah. What's that?
My dad used to tell that.
Oh, really?
Yeah.
Yeah, okay. I know what Dad's going for the groan factor all the time. Right. Okay. All right, but anyway. So, let's take a look at what one of your problems might look like from this. And then we'll get to polarization, and we'll be done with chapter 24. Let's see. I really like, because astronomers use this all the time to measure using the Hubble telescope. They use this all the time for this. Oh my. I did a good job of drawing it on my actual notes. No, this isn't SpongeBob's friend. But this is supposed to be a spiraling galaxy kind of going this way. All right. They'll get a velocity here, or they'll get a frequency over here, and then they'll get a frequency over here, and they can tell, since this is moving away, this is moving away and this is going toward, they can tell how that universe is spiraling. Okay? They can get an idea of the spiral of the thing, and they can also get an idea of what the black hole in the middle of that galaxy is, due to how their ends and what the gravitational, good old mv squared over r stuff. Okay? So that's what astronomers use this for. Okay? So let's look at an astronomy problem then. And that would be problem 31, which says this. Problem 31 says, a distant galaxy emits light that has a wavelength of 434.1 nanometers. 434.1 nanometers. Okay? I'm kind of glad we're going to do this because you need to learn a few little tricks of the trade. Right? And then on Earth, the wavelength of light is measured as 438.6 nanometers. You think their equipment's pretty calibrated pretty close? 434 nanometers, 400. Now, I didn't put anything on here. Which one is the source and which one is the observer? First one is the source. Good. So Fs equals this. And we'd also say this. We'd say 434.1 times 10 to the negative 9 meters. That's a nanometer.
That's not frequency.
That's not frequency, it's still lambda.
That's lambda. It's in meters.
Oh, yeah. Oh, yeah, because that's a key part of the whole thing. There's lambda, the source. Meters. So that one was right. So meters was right. Frequency was way wrong. Sorry. And then this is lambda of the observer. And we'd rewrite this one as 438.6 times 10 to the negative 9 meters. It is lambda. Okay. We need freaks. Is there any way to get, in other words, all right, now here's the question. Decide whether the galaxy is approaching or receding from the Earth and give your reasoning. And find the speed of the galaxy relative to the Earth. So what we're going to do is we're going to go fishing for this VREL out of here, this relative velocity. But first we've got to decide, though, if it's plus or minus here before we can find out what this guy is. Well, let's take a look. Let's take a look. Let's just take a look at the equation and see if we can build on it. Let's take a look at this equation. We got FO equals FS times 1 plus or minus VREL divided by C. Okay. If FO comes out to be, if by doing, I'm going to manipulate these wavelengths so that I can get a frequency. And if FO is greater than Fs, do we use plus or minus? We'd have to use plus, right? Because we want 1 times point something. 1 point something. In other words, we gotta make him bigger. So we gotta multiply him by a number bigger than 1. Okay? You see that? We need plus. Okay? If F naught is less than Fs, if F naught is less than Fs, then what should we use? Yeah, we use minus because we want to shrink him. So to shrink him, we got to multiply him by a number less than 1. So we do this. We do minus. So let's figure out what FO is. Let's figure out what FO is. Well, lambda naught, I'm sorry, I have to do it this way. C equals lambda naught times FO. Or FO, F lambda, whatever. Okay? So FO is equal to C over lambda naught. Fs then would be C over lambda s. Which one of these is bigger? Well, this number is smaller than we're dividing the speed of light but it's the same in both of them. So if this number is bigger, which it is, then FO is smaller than this guy. So since it's minus, it's going away. Since it's minus, it is going away. Okay. And then the rest of it is just algebra. So now that you know, and you actually have numbers for that, you could just go, well, they did it this way. You can just go 1 over lambda naught equals 1 over lambda s times 1 plus v rel. Wait, I went through all that, I still put a plus sign there. There we go. Okay. So all I did was divide out the c's. Just divided out the c's. Okay? And then you can go find VREL. Easy enough. Just get a number here, a number here. 1 minus. You can do it. Okay. All right. Now then, let's talk about one last thing. And I actually looked this up. We're going to find out about polarization here. This chapter is kind of screwy. Okay, we've got this thing with waves. Now let's talk about polarization. Okay? And because electromagnetic waves are transverse waves, in other words, because the E field and the B field move perpendicular to the direction of the wave, they're perpendicular to its velocity vector, basically. Okay, I can polarize light. In other words, I can grab certain materials. I can use certain materials so that I can decrease its intensity by quite a bit. All right. In fact, if I take, here's the deal. Here's how this works. Let me just go through it. Okay. If I take polarizing material, I want to make sure I get the terminology right. Okay. Have a polarizer, then an analyzer. All right. Here's basically what happens. Let's say, see this slit in the door? I'm going to open this up. This reminds me. I had an inspiration here. See this slit in the door right here? Okay. Let's say I got Alex on the other side. The window's not in there, and I got Alex on the other side, and she's holding one end of a rope, and I'm holding the other end of a rope. Okay, and she's out in the hallway. And we go like this. Will it, as long as we kind of keep the amplitude not bigger than the slit in the door, won't the rope just have a nice little wave like that and move along? Well, what happens if all of a sudden we turn the window, or we want to go like this, do this wave? Can we do this wave? No. But if the door is open, I can do this wave, I can do this wave. I mean, I can go all kinds of angles. I can go any angle I want. Okay? But if I just have this one slit, this is what polarizers do, is they keep, they wipe out all the other waves, okay, except for they let one get through. All right? And by experiment, what they found is you got the original average intensity coming out. Okay, you got the original average intensity. I put a polarizer, and I get a new intensity. This is polarized. Okay, this is polarized, and when it's and that equals S polarized equals 1/2 the original intensity. It makes no difference. It makes no difference what the orientation is of the polarizer, okay, on the first, with the first one, okay? It's when you put another it's when you slide another piece of glass in. In other words, we turn this thing sideways, okay? So now I can only do it this way, okay? Or a little bit this way, and a little bit that way, okay? But now, if I add another one that just allows me to go the little bit the one way, then that's when you have to deal with the angle of orientation. That's for the analyzer. Polarizer, basically here's the deal. Polarizer takes half. Takes half. I put another polarizing material in there, and it's got a certain orientation, which will be given to you. Okay? The analyzer takes S okay, so the polarizer takes half, the analyzer takes S cosine of theta squared. I wrote it that way just because that's the same thing. I don't, the book writes it the traditional way like this. I like doing it this way so that there's no confusion. All right. I'm going to put underneath here regardless of orientation. Okay? The analyzer depends on the orientation. Okay, now here's the deal. Here's something kind of strange then. Okay, so let's say I got a polarized light. It takes half. Let's say I take another piece of polarizing material and rotate it at a complete 90-degree angle. The analyzer is now at 90 degrees. The analyzer is now 90 degrees to this to the polarizer. What is the cosine of 90? 0. So guess what I've done? I've blocked it out. I've made it black. Okay? And that's how LEDs work. It's a bunch of you got all these little polarizing agents in there based on the computer code that you're given. Like when I punch a 1, it says, oh, I'll polarize all this stuff this way, block out everything except for this little bit that's coming out here. That's the way it works. The only way that could work was with semiconductors. All right. So if you take a pair of Polaroid sunglasses, lay them down on something, you'll see, like if you not on a white surface, but if you lay down on a red striped surface or something like that, then take a second pair and lay them over it, and then rotate them at 90 degrees, and it'll be black. Nothing will come out. Okay. They show an example of that in the book, but I think it's in drawings, so you may or may not believe it. All right. Okay. So let's take a look at your homework problem that I've assigned from this mess. Okay? Or I'll give you one that's just like it. I'll give you one that's just like it. Okay. Basically what I have is I have a polarizer and 2 analyzers. Okay? I've got a polarizer and 2 analyzers. Got a polarizer and 2 analyzers. Polarizer and 2 analyzers. Okay? The polarizer is at, so I've got A1 and A2 and P. The polarizer is at an angle of, this isn't your homework problem, but it's just like it, 30 degrees. This is at which I haven't even put your homework assignment on there yet, but it'll be there, I promise. This is at 70 degrees. Okay, so let's take a look from the front. If we're gazing at this thing from the front, I've got my polarizer at 30 degrees. He's oriented at the 30-degree angle. Analyzer 1 is at 45, and analyzer 2 is at 70. This is my polarizer. Okay, the original intensity coming in, the average intensity is 1,555 watts per meter squared. That's the average intensity coming. That's the original intensity. What we want to do is find the intensity of the beam transmitted through these 3 sheets. Okay? What we want to do is we want to find the intensity of the beam transmitted through these 3 sheets. So we break it down into, it goes through the polarizer, then it hits the analyzer, and then it hits analyzer 2. All right. Now then, it's coming through this polarizer. Do I worry about this 30-degree orientation for the polarizer? No, I don't. So I say this. S of P equals 1/2 SO. I'm going to change this problem, make it 1,500. Because I can. There we go. Make that 1,500. All right. So SP then equals 750 watts per meter squared. Okay, not bad. Now then, as it's coming out of, now it comes right out of analyzer 1. What is the orientation? So for analyze, the intensity coming out of 1 would equal SP times the cosine of some angle squared. Okay? Times the cosine of some angle. Okay, so what's the angle going to be? If this whole thing was 45, do I put 45 there or what? What do you think? You'd put 15. Exactly. You go 45. It's 45 minus 30, which goes to 15. You put the 15 degrees in there. Okay? And so that equals, well, now I can't do that one in my head. Sorry. I don't know what the pi over 12 squared is. I know it's pi squared over 144 times 750. It's about 6 times 10. It's probably around 600.
724.
It's 724? Okay. All right. See, because it's kind of intense. It still keeps it, because the angle's not that big. As this angle gets bigger and bigger, the intensity goes down until I get it, until if I was oriented right here, it would be black. Come out black. Okay. And then finally, as it's coming out of SA2, this would be SA1 times the cosine of some angle squared. What would that angle be? We're coming out of here now. So this was 45. This was at 70. So we're just going to look at this angle here, this orientation here. Because it's coming out of here, which is at half. Then we look at this orientation right here. Now we look at this one. So that looks like it's 70 minus 45, because that whole thing was 70. So that'd be 35. And that gives you the whole thing. You could do it in one equation. You could just say, oh, well, I know that it's coming out of SA2, if you've done this stuff 100,000 times, of 1/2 SO times cosine of 15 squared times the cosine of 35 squared. 25, yeah. There you go. Seventy minus 45. 70 minus 45. Do 25. Okay. Whew. Speaking of intensity, that's a lot of stuff. That's a lot of stuff. But the two homework problems from, well, we did one. Basically did one. Your numbers will change on Wiley Plus. And then we did this one, which will be like the one I'll give you on Wiley Plus too. So I'll just give you like 5 or 6 problems from chapter 24 to do. And Rachel, here's your test.